Thank you very much. I would like to thank all my co-authors who worked with me on this subject, but particularly Alain, who is not just co-author, also a friend, and for this opportunity to be here, for the invitation. I do appreciate it. Now, Plato was one of the most significant philosophers of ancient Greece, and his ideas are still with us. In the Western world, we still think influenced by Plato, or at least we hope we do. One of his most remarkable theories was about pairing the elements which were in the Greek thinking the phases of matter to the regular solids. Now, the phases of matter in Greek thinking were the earth, the fire, water, and air. And the fifth one, because there were 5 regular solids, the fifth he associated with the universe. The regular solids were known to the Greek mathematicians. In fact, the 13th book of Euclid is mostly dedicated to the proof that there are exactly 5 regular convex polyhedra, so where each face is a regular polygon, identical, and each vertex is identical. So they proved it. But Plato was the one who realized the potential philosophical implication of this statement. From the combinatorial point of view, we have 2 types. We have 2 types of these regular polyhedra. 3 of them are called simplicial because they have triangular faces. And 3 of them are called simple because their vertices are of degree 3. As you can see, the tetrahedron is both because it has triangular faces and at each vertex 3 edges meet. For the other ones, it is either simplicial or simple. Plato's theory that matter consisted of these regular solids was immediately met by a very strict criticism from his own student, Aristotle. And Aristotle said that this theory cannot be right for a simple reason. You cannot fill space with regular solids. He said that out of the 5 solids which Plato claimed were the building blocks of matter, only 2 fill space, the cube, which was associated with the Earth, and the tetrahedron. Now, let us have a quick look what is meant by space filling. How many regular polygons do we have in the plane? How many regular polygons do we have? I invite comments from the audience. So we have a regular triangle, regular rectangle, infinitely many, thank you, yes. We have infinitely many regular polygons, but only 3 of them can tile this plane. The triangle, the rectangle, and the hexagon. There is no other regular polygon which is tiling the plane. Now here are the solids, and as we know all, the cube can tile space. That is familiar to everyone. And if we tile space with cubes, at each point, 8 cubes will meet in this tiling. You can see this on this small figure. Now, Aristotle claimed that the tetrahedron can also tile space. How many tetrahedra can meet in a tiling at one point? Anybody would like to venture to give an estimate? It doesn't have to be right, but who said 24? That was actually Aristotle's thought. So 24 was probably his idea. The truth is actually 22.79. So this sparked the debate about spatial angles, which lasted for 15 centuries. It was a very fruitful debate. None of the others fill space. So, for example, the octahedron doesn't fill space, doesn't tile space. On the other hand, there are solids which are called semi-regular, which can be produced by truncation of the regular solid. So here is a regular octahedron. And if we chop off the vertices at the third points of the edges, we get something which is called a truncated octahedron. This is also a famous polyhedron in its own right. Now, the huge difference between the octahedron and the truncated octahedron is that the truncated octahedron does tile space. So there are space tiling polyhedra, not the regular ones. Now, despite the shortcomings of this theory, there were people who vehemently defended Plato. And two gentlemen of this group are Frank Wilczek and Werner Heisenberg, both having the Nobel Prize in Physics. And the reason why they defended Plato was that, according to Wilczek and Heisenberg, Plato's message is that matter consists of very small, identical, symmetrical objects. And they argue that this is the root of our atomistic picture of the world. And in that sense, Plato was right. Today, what I would like to show you that he may have been right even more directly, not just in a metaphorical sense. As you can see, the cube was associated with the Earth. Now, here we see a video, which was, this is the middle part of the United States, and we are zooming in on a cliff. And as you can observe, the line of the cliff is not smooth. In particular, it is a kind of a zigzag line. And if we go closer, we observe that the shapes which this cliff consists of are actually cubes, not small ones. So these cubes are several meters in diameter. Here you can see a person standing on such a cube. So in this case, in this particular case, Plato appears to be right, because Earth consists of cubes. But if we go out and collect fractured rock, we don't see the cube. This has been collected near Budapest, Dolomite rock. We collected a couple dozen, we brought it home, and we scanned these objects. They are not cubic. However, they are polyhedral. So they have flat faces, sharp corners, and edges. You can observe it yourself. You can collect them yourself. Since they are polyhedra, they can be well approximated by polyhedra, not the regular ones, irregular ones. And for each polyhedron, we can count the number of faces and vertices. Now, this is good because it gives us some kind of solid footing. In this case, the average was 6.4 for the faces and 8.6 for the vertices, which is reasonably close to the cube. So we went back and we collected 556 fragments and did the counting again. And for those, we found an average 6.03 and 8.01. Now, even outside geology, this is good match. In geology, this is too good to be true. Now, we also observed, so it looks that the cube is there, but not in a visible form. We observed that the cracks were long and straight, which caused this kind of fragmentation. This is another rock face in Finland, a granite rock face. Again, you can see these long, straight lines. The mathematical model to describe this kind of pattern is called a convex mosaic. A convex mosaic is tiling of the plane by polygons. A very simple tiling is just a rectangular mesh. This is a more complicated tiling. So we have polygons, And the degree, they are called cells, and the degree of the cells is just the number of corners. And we have nodes, and at the nodes, the degree of the node is the number of corners which meet at that node. There are two types of nodes. This is a regular one, and there are irregular ones where corners sit on edges. Here, corners are sitting on corners. If we have a mosaic, we can count these numbers and we can take the average. The averages are spanning a plane, and each mosaic associated with a point on that plane. These we call the symbolic plane. So here is the symbolic plane, and here are some patterns and the corresponding point on the plane. For example, this is the rectangular mesh. Each cell is of degree 4, and each node is of degree 4. So this is 4, 4. This is a honeycomb. Each cell is of degree 6, and each node is of degree 3. So this is 3 and 6. Now, on this line, on this hyperbola, all patterns which sit here are regular, so they are face-to-face. Corners only meet corners. Here we see like the brick wall, where corners are sitting on edges. Back to the granite wall. This is a very special type of mosaic. It is created by straight lines. And now I tell you one theorem. So if this domain is big enough, then I claim that the number of cells and nodes is equal, if it is sufficiently big. So if we neglect the boundaries. And the proof, I tell you that the proof, this is the only proof I tell you. The proof is simple, because what we do, we take just one cell, and we imagine that this is between two glass plates. And this is a container, and we put a little bit of water into this container, just very small amount of water. How many corners of that cell will be wet? Very small amount of water, even just one drop of water. How many corners will become wet? Just one, just one. Now, all the nodes are like X nodes because they are created by intersection of two straight lines. How many corners of an X node will be wet? How many corners can hold water? Just one. And in mathematics, this is called a mutually one-to-one relationship. And that means that there are same number of corners, same number of nodes and cells. Now, this simple fact is true in any dimension. It's true in 2 dimensions, 3 dimensions, any dimension. And from this, it follows that if we take such a mosaic in any dimension, the average numbers associated with the cells will be identical to that of the d-dimensional cube. So this is very simple mathematics, and it suggests that if we have a fragmentation pattern like this, indeed, we will count the number of faces and vertices. We should get numbers very close to those of the cube. So we checked it a little bit because we were very cautious. Again, so this is the experiment. And here I plot not only the average, but also the distribution of the number of faces and the distribution of the number of vertices. And then we created some fragments by computer, a little more, 600,000, because it's cheap. And this is the distribution for the computer fragments, and the overlay is pretty good. Does anybody has a question at this point? Because there is something funny on one diagram. So you can see that this diagram has one hump. This is a zigzag line. That's very strange. The zigzag line is strange. I showed you that 3 of the regular solids were simple polyhedra. Simple polyhedra have vertices of degree 3. Now, if you create polyhedra by this kind of process, you create simple polyhedra. So this process will always create simple polyhedra. And simple polyhedra have the property that the number of vertices is an even number. So there is a strong bias towards even versus odd. So nature tells us, based on these small observations, that this is probably the right model. So maybe Plato was right. We don't know. His philosophy was always that what you see with your naked eye is not the truth. You have to see beyond that. You have to do something with your mind. Here, the act which we do with our mind is averaging. Here are a few natural patterns. On the left corner, you see Mars. This is basalt columns. This is mud. This is the permafrost in Alaska. This is the rock where the ultimate scene of Mission Impossible 6 was fought. It's a granite rock. And this is again mud. And we plotted these things here in the symbolic plane. There is one additional mosaic, which is the tectonic mosaic. So we are on large scale. And this is a mosaic of the tectonic plates as cells on the Earth, and a pretty large mosaic. Now, as you can see, this is number 15. It is almost here at the tip, but it is not quite at the tip. The reason that this mosaic is not at the tip, because this is a spherical mosaic. It is not a planar mosaic, and the rules are slightly different. If it would be planar, it would be at the very tip, top. Now, as you can see, all natural mosaics appear above this line. So the cell degree appears to be equal or larger than 4. What is here? Why does nature avoid mosaics which are below that line? Again, here we have regular tilings. Here is this area where all mosaics, all convex mosaics are in this area. So what is outside this area? Above, we have non-convex mosaics. Here we have hyperbolic mosaics. And we don't know what is below them. Certainly, if we go below, we have to reduce the number of vertices. How can we do that? Here is a rectangular mesh, and we start bending this mesh. If we start bending the mesh, we get rid of corners. Now, how long can I do this? Here you see in this cell we have already 3 corners only. And here also only 3 corners. Where do I stop? So how far can we go? You may have observed that there's a bottle of wine here on the table. I'm sure you have observed. This wine I brought for Dyrol in appreciation of his brilliant heart to organize this talk. And there were 2 reasons. This is a high-grade Hungarian wine. The other reason I brought it is a deeper reason, because in Budapest airport, if you buy wine, they package it in a particular way. They give you this thing. And I invite you to come to Budapest. And if you look at this, this is the same pattern which you see. It is not nature, but we will get there. So these tiles have 2 corners. And now I give a definition. In any dimension, there is a certain minimal number of vertices which we need to tile that space. I don't tell what is this minimum yet, but I say if we achieve that minimum, then we call that a soft tiling. So if we are at the minimum, we call it a soft tiling, and we call those cells which have this minimal number soft cells. in 2 dimensions, we have a theorem saying that this minimal number is 2 minus a complicated formula. Luckily, if we are on the Euclidean plane and we are looking for infinite tilings, this is 0. So on the Euclidean plane, the minimum is 2. And this is a lower bound, but I showed you that this is a sharp bound because you can actually achieve it. You can make tiles which have just 2 sharp corners. So now we know what is below here. There are soft tilings. Here is a picture of the symbolic plane with many, many soft tilings. Here you can see, oh, I zoom in. So here you can see, for example, if you put down circles, and the circles have no corners at all, okay? But the little spaces between the circles have 4 corners. So on average, we will have 2 corners. So that's also a soft tiling. These are examples of soft tilings. And we notice that these tilings pop up in nature and in other places. So here are geometric soft tilings, and here are some examples. This is muscle tissue. This is an onion. These are blood cells, sterling. This is a zebra. And on the right column, you can see buildings by Zaha Hadid, who was called a prominent architect who died recently. She was called the Queen of Curves. So she tried to avoid corners in her design. And instinctively, apparently, she found soft cells in the design of the facades. Now, soft cells come in all sizes. The title of my talk was Hard Rock and Soft Cells. Now I show you soft rock and soft cells. This is work in progress with Christoph von Hacke. So this is the coast of Brazil. And if we look at the geological map of the region, we can see the shear bands, these fault lines. And they show us that they emerge in soft cells. So rock, at high energy, high pressure, rock becomes soft. And as a soft material, it arranges itself in soft patterns. So we can see soft cells on various scales. What's happening in 3D? Now, in 3D, we know much less about tilings in general. This is the symbolic plane. Here you can see the regular tilings in 2 dimensions, which I showed you earlier. So just the regular ones. Here I plotted the best known 3-dimensional polyhedral tilings, which are called uniform tilings. There are 28 of them. And they seem to be arranged along a line, a curve, but they are not. So this is not experimental data. This is mathematical tilings. And they are quite close to this curve, but they're not on the curve. So we have a conjecture that they are constrained by 2 curves. It is not proven. There are examples of 3D tilings. This is what I showed you earlier. This is a primitive tiling which we use to illustrate Plato's theory. This is like a basalt column tiling, and there are others. Now, here were 2-dimensional soft tilings with exactly 2 corners. And in 3 dimensions, the analogous theorem says that the minimal number of vertices you need is 0. And to prove it, it's very simple because I just have to show you 2 examples. These are shapes which tile space, but have no corners at all. And here, one of them is on the table. You can see it. And this is the way how it is being matched. And you can imagine that I can build a rectangular prism out of this, and I can put this prism next to each other. So this is actually a space filling. It is relatively easy to find out. Now, this is a tetrahedron distorted in this manner. So how do we get these shapes? First of all, let me say that the soft tilings in 3D are sitting here at the origin. So there is no going beyond that. They have 0 corners, both in the cell degree and also in the nodal degree. How do we make something soft? Well, it appears to be very easy. You take a cube and you start bending the edges and you get rid of the corners. And if you do it for a while, you end up with something which is a soft shape. So what is wrong with this shape? Why is this shape not good for my purpose? What is the fundamentally wrong with this shape? Yes? I'm sorry?
It won't tile the plane. No.
It will not tile space. Yeah.
Yes.
Yeah, it is not that it will not tile space. It is soft. You can take a sphere. It's soft, but it doesn't tile space. So to get to a space-filling tiling, which is soft, you have to apply some kind of strategy. And this strategy is about taking a polyhedral tiling and bending the edges in a systematic way. Now, bending the edges of polyhedra is not new in natural science. Here are dry forms, and Lord Kelvin conjectured, you are familiar now with the truncated octahedron. I have shown you. So this is the truncated octahedron, and he conjectured that the best optimal space-filling shape, which is the model for dry forms, is something which is close to this shape but not quite identical. So we take this shape and we bend the edges slightly. Why? Because according to the laws of Plato, who is not identical to Plato, these edges have to meet at equal angles, the edges. And in order to achieve equal angles, you have to bend them slightly. So you end up with this kind of, there is no analytical description of this object, and it is not proven yet that this is the best. We know a better space filling with 2 objects, the Verfällen, but for one shape filling space, the best surface to volume ratio is still believed to be this, conjectured by Lord Kelvin. So bending edges is a good idea. But we go much further. So we designed an algorithm which we call the edge bending algorithm, which does this edge bending in a smart and systematic way. So we focus on one node, and this algorithm lets you color the edges in 2, like red and blue. And the rule is that red edges have to be aligned with red edges, and blue edges have to be aligned with blue edges. And if you do this for all nodes simultaneously, then you end up with a shape, and you can smooth this shape a little bit to get less wiggly edges, and you get the space-filling soft cell. So the edge bending algorithm is about creating out of polyhedral tilings, soft tilings. And almost in every case you can do that. So this is a theorem. So for almost every polyhedral tiling, certainly for everyone which we know, you can do this. There is a combinatorial restriction which may not be necessary. Now, this is the cross-section of the shell of the Nautilus. The Nautilus is an iconic animal. I would call it a living fossil. It is the only relative of the ammonites which dominated the seas a couple of 100 million years ago. And this became famous because of the center line is a logarithmic spiral. It is on the cover of the book on growth on form, which was written by Darcy Thompson, and it is a classic on biological growth. Now, we are interested in the three-dimensional structure. Look at this shape. This has two corners, and it tiles the shell. The fact that it is spiral is not really relevant. You could do this among parallel walls. So in 2 dimensions, this is a soft tiling. But what happens in 3 dimensions? Here is the shell, and we filled in digitally the chamber. Now, the chamber is a very particular shape, and it appears to have no corners at all. So if you have constrained growth and you have to fill space, then obviously biological growth doesn't like sharp corners, tries to avoid these corners, and produces soft cells spontaneously. Here you can see the 3D view of this beautiful shell. And here is a geometric model of a space-filling soft cell, which is a geometric analogy of the chamber of the Nautilus. Let us return now to the truncated octahedron. As I showed you, the truncated octahedron fills space. It's a polyhedron which produces a tiling. And one can make a soft tiling out of this. And this is the result of, if we apply the edge banding to this tiling, we get this shape. Here are 2 copies of this shape. Would anybody volunteer to come and match these shapes? Just match them. Yeah, we got somebody? Please. I invite you to stand here so the audience can see you somewhere. Yeah, I hope the camera is right. Yeah, just try to match them.
Okay.
That is good, yeah. Okay. Please show it to the, yeah, exactly. Small applause, thank you. Thank you very much, thank you. So this is a soft tiling now, made out of the truncated octahedron. Why do I say it made out of it? Because the vertices are the same. I didn't touch the vertices, I just bent the edges. We say that it is first order identical. Now, what did I change? I changed the edges. The edges are defined by the tangents. Because this is a highly symmetric object, it is sufficient to talk about just one tangent. One tangent will define all other tangents. So you can see that here the tangent is horizontal, here the tangent is not horizontal. So I'm bending the edges simultaneously. I'm bending all edges. Now, there is an interesting statement claiming that there is a second version of this somewhere out there. And this octahedron can be bent into a soft tiling in 2 different ways, exactly 2 different ways. One of them you already saw. And now, before I uncage this second version, I have to tell you something, a little bit of background, because this is surprising. So, triply periodic minimal surfaces are geometrical miracles. Imagine a plane. A plane divides space into 2 half spaces. If the plane is a little bit wiggly, we still got a clear idea how it divides space. Bernard Riemann, whose ideas changed science, I could say, not just geometry, was the first to dream or to envision an object which is a surface which does not intersect itself. So it is like a plane, with no intersection, but it extends not just in 2 directions, but in 3, in all 3 directions of space. And it divides space into 2 parts. But those parts are startling. each of those parts is a labyrinth of tubes. If you can't imagine it, I don't blame you. There are very few people at all who can imagine this, and there was only one person who could imagine this so that nobody knew about it. Let me show you very close to Riemann. Schwarz independently also derived several of these surfaces, and they are named after him, the first ones. So here is one surface. This is the Schwarz D surface. So it extends in every direction. You don't have to understand this at the first sight. It is very difficult to digest, but you will see that it is worthwhile to think about it. And here is another one. This is the Schwarz P surface. Now, as with always with science, there are these great ideas like Riemann and Schwarz, but we had to wait many years, more than a century, to understand the application. And in general, one should be patient with ideas. So many of you might have heard about graphene. Who has heard about graphene? Everyone, okay? And graphene is a wonder material, it's superconductivity, it's an allotrope of carbon. There is another version of another carbon allotrope, which is called fullerene, you might have heard of, which are like graphene in a sphere, basically. Now, recently, physicists, chemists have identified a third version. For geometers in the room, this will be the natural thing. This has no curvature. It is a plane. This has positive curvature. There is a third version with negative curvature. And the third allotrope is called a Schwarzite, because it is sitting on a Schwarzian triply periodic minimal surface. And it has negative curvature. This has fundamental impact on material science. We are still in the process to understand these materials. So, what does it have to do with tilings, these surfaces? Because now I am talking about tilings. So there are these labyrinths, and the Schwarz P surface is built around a labyrinth which can be collapsed onto a rectangular grid like this. But there is a second grid which is shifted, and both grids have equal rights. Now, to understand this, I show you a photo, and this is made of concrete. So this is the Schwarz P surface built of concrete elements. And based on the photo, you understand that there are two labyrinths, not just one. If you enter on level 1, you can exit on level 3, but you cannot exit on level 2. So these labyrinths are independent, and they go all over space. The Schwarz P surface is the most simple example where a human can hope to understand what is the making of a triply periodic minimal surface. For me, this was the only one. And now you can see on the very same picture that these labyrinths can be divided into equal cells. Do they have corners? No. They are soft cells. So the building blocks of this surface are soft cells. Now we come back here, and that is no surprise anymore that the brother of this object, which you matched brilliantly, is the building block, the unit cell of the Schwarz P surface. So these minimal surfaces are now connected to polyhedra and to other soft tilings by this theory. Well, you can see that we generate this family by turning the tangent. By turning one tangent, I turn all tangents by symmetry simultaneously. I just drew one tangent but as I turn one tangent, I bend one edge, all edges are being bent simultaneously. And as we travel from this cell to the polyhedron and then to the Schwarz P surface, we hit another interesting point, and that is the Kelvin cell. So the Kelvin cell, which Lord Kelvin conjectured to be the building block of dry forms, is part of this family. It's not soft, it has corners, but soft cells kind of embrace it or explain it a little bit, how it is being generated. Well, we can turn the tangent not just in the plane, but all around the sphere, and we can generate other cells like this in this method. And we can find connections to other soft cells associated with other surfaces. So one of these surfaces is the Schwarz D surface, and another famous surface is the gyroid. Both of them are triply periodic minima surfaces. There are not so many triply periodic minima surfaces we know. I think there are like 19. Each of them is very significant. The gyroid is one of the most celebrated and most mysterious. Among them, it was discovered by Alan Hugh Schoen, who recently died. And we still don't understand fully the combinatorial properties of the gyroid. Nevertheless, every single such thing is built from soft cells. Now, there are different kinds of soft cells. This is the Schwarz P. Anyone would like to match the Schwarz P to itself, to its pair? You are welcome. Yeah, please. Yeah, come. There are several. Come. Yeah. So please do this, and so that in front of the camera, this is the camera, so people can see you. And yeah. There are other cells. Yeah. Let me check whether this. Oh, this is very good, very good. There is another way to match it. Yes. So there are two ways. One matching corresponds to the case where you are in the same labyrinth, and the other matching corresponds when you are in the other labyrinth. This is the gyroid. Again, you can match it in two different ways. Try. I showed you one. Okay. Try it and show to everyone. Yeah, please. Go to the camera. Go to the camera. Yeah. I'm sorry? This is one matching. Yeah, this is when you are in the same. If you are in the same labyrinth, then you are matching these planar faces. Then you create one tubular labyrinth. But then you have to. Then what happens if you are in two different labyrinths? How can you match them? You are not allowed to match circular faces. You have to match these things.
Oh, this.
Oh, yeah.
Oh. Ooh.
Yeah.
This.
Yeah, with the saddles, maybe like this.
Oh.
Try.
Like this.
Yeah. Turn it a little bit. So there you go. Thank you very much. So I think I can also speak on behalf of Alain that we are very far from understanding soft cells. What we see that they pop up in surprising places. They pop up in the shells of sea animals. They pop up in microstructure. They pop up on very large scale in geological setting. So we don't know yet where we go from here, but we feel that these objects help to describe certain phenomena in biology and physics, and they are helpful to match and to connect different geometric objects. Let me mention that there are other. So if you have one triply periodic minimal surface, you can create not just one soft tiling, but several soft tilings. For the Schwarz D surface, and here, this is a copolymer. So this is a special version of a polymer, two components. And this is a cell from a Schwarz D surface. And physicists have now described the geometry of these polymers by using these objects. They call them mesoatoms. They are soft cells. And this kind of copolymer is built from mesoatoms from the Schwarz D surface and from the G-ray, the ones which you successfully just matched. So they are part of material science. So here you can see a couple of these cells. And the most difficult one, which is here, is a very, very strange decomposition of the Schwarz D surface. I didn't dare to ask the audience, but luckily we have a professional in the first row, and I would like to thank Sir Roger for putting it into the right position. Much faster, actually, than I did. And just an announcement on May 29th. So this is this soft cell, but it was on the poster designed by Dyrol in a skeletal format. So it is just a skeleton. This skeleton will travel to space. On May 29th, we have a liftoff of a NASA mission to the International Space Station. And this will include some experiments. One of the experiments will include this skeleton. And the reason is the following. As you can see in the beautiful picture which Dyrol used for the image, for the poster, there are soap bubbles. The smooth parts of the soft cells are minimal surfaces. And if you take a skeleton and you put it into soap solution, you get these bubbles, and they give you the minimal surfaces. Now, what happens in space? In space, there is no gravity. They will go to the International Space Station. And if there is no gravity, water assumes a shape, the border of which is a minimal surface. So if you just throw up a little bit of water, it will be spherical. However, if there is a skeleton like this, which by surface tension is kind of guiding water, how to attach, to which it can attach itself, we hope that what we will see will be a soft cell made of solid water. So water will be inside the skeleton, and the outer faces will be free water surfaces. We will see how it goes. We are very fortunate that we have a Hungarian astronaut on board. And we are also very fortunate that the commander is Peggy Whitson, who is the most experienced astronaut currently, and she is personally supervising this experiment. Anyway, thank you very much for the attention, and I'm very happy to take questions.